Okay, this is section 17.5, factors affecting solubility. So we're going to look at two ways in which we can affect the solubility of one of the salts that we talked about in the earlier section, 17.4. And the first factor we're going to look at is the common ion effect. We talked about that early in the chapter when we were talking about buffers. This is also a factor when it comes to solubility. So I'm going to take the example of silver chloride. Silver chloride has a modest solubility. It's pretty low in water at room temperature. The KSP, we can look that up, and it's 1.6 times 10 to the minus 10. Of course, the KSP is the concentration of silver ions times the concentration of chloride ions, right? That would be KSP. Okay? So there you go, KSP, silver concentration times chloride concentration. So let's find the molar solubility of silver chloride first, and then we'll deal with the common ion effect. So let's do our ice table. These are initially 0. Q therefore is 0, so that means the reaction goes toward the right. So at equilibrium we have S and S. Those are the concentrations. So KSP is really S squared, right? S times S, S squared. So that means that S is the square root of KSP. So that would be the square root of 1.6 times 10 to the minus 10, which is probably around 1.3 times 10 to the minus 5. So 1.6 times 10 to the minus 10. Let's take the square root of that. It's around 1.3 times 10 to the minus 5. That's the molar solubility. Okay, so let's interpret the physical meaning of this. We shouldn't lose sight of that. What that means is, if you have 1 liter of solution, 1,000 milliliters, okay, half of a 2-liter bottle, that means that 1.3 times 10 to the minus 5 moles of silver chloride will dissolve into that liter. That's the maximum amount at room temperature you can get to dissolve. Any more than that, it will precipitate out at the bottom. Okay? That's the maximum holding potential, if you want to think of it that way. The maximum that the solution can handle, the water can handle, before the silver chloride starts to precipitate. Now what we want to do is we're going to do the following. We're going to add a little bit of silver nitrate to the solution. Okay? 0.10 molar. Now it turns out 0.10 molar is actually a pretty high concentration, but I want to show you the effect of this. Silver nitrate is a nitrate, which means that it is very soluble in water. So if we try to dissolve 0.1 moles of silver nitrate into a liter of water, it will all dissolve, resulting in the formation of 2 ions. Put it into water, it all dissolves, the silver ion and the nitrate ion. Now silver is the key here. Silver is one of the ions in this equilibrium, right? So that would be called a common ion. Nitrate is not particularly important here. We would call it a spectator ion. But the silver is certainly a common ion. It's common to this equilibrium. It's in that expression. Okay? So what we're going to do is we're going to dissolve the silver nitrate to make it 0.1 molar. Now that affects the equilibrium of silver chloride. And I'll show you how. See, instead of this being 0 initially, it's 0.10 now because all the silver nitrate dissolved, so you have 0.10 molar. This is still 0 here, right? We haven't added any chloride. However, Q is still 0 because chloride is 0. So that means we still gain some of these 2 ions, And so at equilibrium, we have 0.10 plus S, and we have S. So KSP would be equal to 0.10 plus S times S. Now, 0.10 plus S, look what we had over here for S. I'm not going to claim that S is going to be the same, but it's going to be pretty small compared to 0.10. So we can simplify this as 0.10 times S, right? We don't need to worry about this S right here. It's too small compared to 0.10. So that means that S is just KSP over 0.10, right? Just divide both sides by 0.10 and you got your S. So 1.6 times 10 to the minus 10, that hasn't changed, over 0.10, and you get 1.6 times 10 to the minus 9. Moles per liter, that's your molar solubility. Now compare that to what we had before. It got a lot smaller. Instead of being 10 to the minus 5, it's now 10 to the minus 9. So what that tells us is that adding a common ion to the solution reduces the solubility of the salt. So adding a common ion to a solution reduces the solubility of the salt or of the compound. It's got to be a common ion. And so there are two possible common ions we could use. We could use chloride. Had we, instead of dissolving 0.1 molar silver nitrate, had we dissolved 0.1 molar sodium chloride, it would have had the same effect, because now we would have had 0.10 plus S over here, and this would have been S over there. It just mathematically would have worked out to be the same answer, 1.6 times 10 to the minus 9. So adding one or both of these common ions will reduce the solubility of the compound we're studying. Okay, that's the common ion effect, and we can describe that in terms of the equilibrium expression. Now, I want to show you a second method of affecting solubility. And to be honest with you, it's actually, in a sense, it is the common ion effect. But it's the issue of pH. So we're going to look at the effect of pH. Okay. Now, on the effect of pH, we're going to use magnesium hydroxide as an example. Magnesium hydroxide is the active ingredient in milk of magnesia. Isn't that interesting? There we go, right? And so let's write down some KSP information. KSP would be the concentration of magnesium times the concentration of hydroxide squared. Is that right? And if we look the value up, okay, we'll find that it's 1.2 times 10 to the minus 11. Just look it up in the table, okay? So there's our KSP, expression for KSP, and the value of KSP, again, at 25 degrees C. Okay, so let's look at the calculating what the pH of this solution would be. Notice that you form hydroxide when it dissolves. So that means hydroxide is being formed. It's going to affect the pH. So let me show you how to calculate the pH here. What I'm going to do is I'm going to say, okay, this is initially 0 and 0. Q is 0, so that means you get plus S. Now notice there's a 2 there, so plus 2S. So at equilibrium, we have S and 2S. So S is the magnesium concentration, 2S is the hydroxide concentration. That would be equal to KSP. Notice the square there? It's because of the square there. So this 2 squared is 4. So this is 4 times S squared, that's S cubed, is KSP. So what I'm going to do is I'm going to solve for S, and that will give us the hydroxide concentration. Okay, divide both sides by 4. Now you take the cube root of both sides. If you take the cube root of s cubed, that gives you s. That would be equal to the cube root of ksp over 4, which is the cube root of 1.2 times 10 to the minus 11 divided by 4. Okay, 1.2 times 10 to the minus 11 divided by 4. Okay, divide that by 4. And then take the cube root. 1.4 times 10 to the minus 4. Okay, I'll use molarity units. Okay, now, here's the question. What is the concentration of magnesium? Well, it's S, right? So that's 1.4 times 10 to the minus 4 molar. What's the concentration of hydroxide? It's 2S, right? So that would be 2 times that. It would be 2.8 times 10 to the minus 4. So that's your hydroxide concentration. So what we could do, since we know the hydroxide concentration, is we could calculate the pOH minus log of the hydroxide concentration minus log 2.8 times 10 to the minus 4. So let's figure that out. Okay, so I'm going to multiply this by 2. And then we're going to take the negative log. 3.54. So what's the pH? 14 minus pOH, right? 14 minus 3.54. So what is that? 10.46? So the pH would be around 10.46. So in other words, although it doesn't form very much hydroxide, 2.8 times 10 to the minus 4, remember it's 2S, that's not a real high concentration, but it is high enough that the pH is going to be somewhat basic. pH 10.46, significantly basic, in fact. pH 7 is neutral. So it's quite a bit. Okay, so that's one issue that can come up. Now, here's what I'm going to do. I'm going to ask, suppose that we change this around a little bit. Suppose we said what we're going to do is we're going to make the pH be a certain value. We could use a buffer, for example, right? There we go. Okay. So let's say we make the pH four using a buffer. The question is, what happens to the molar solubility? Does this become more soluble or less soluble if the pH is 4? So let me show you how we would deal with this. Since the pH is 4, the pOH would be 14 minus 4, right? pH plus pOH equals pW, which is 14. So there's your pH, 10.0, which means the concentration of hydroxide would be 10 to the minus pOH, which would be 10 to the minus 10, which is 1 times 10 to the minus 10. Let's not worry about sig figs for right now. So that is the concentration of the hydroxide. So what I'm going to do is I'm going to rewrite our expression here for equilibrium. And I'm going to indicate that this one right here is 1 times 10 to the minus 10 molar, right? Because the pOH is 10, so that means that's what the concentration is. So now, let's see what the effect of this is. This is initially 0. Now this is 0, so that means this is going to go up a little bit. This is going to go up by a little bit as well, right? 2s. And so at equilibrium, we'll have s, and we'll have 1 times 10 to the minus 10 plus 2s. Okay? So now KSP would be magnesium concentration. We looked at that earlier, right? It's S times the hydroxide concentration squared. Okay? Now, here's a little issue that arises with this particular problem, which is that the solubility actually might now actually be pretty large compared to 1 times 10 to the minus 10, right? Like before we had high concentrations, and this one is a very low concentration. So what we might find here is that we would have to approach this problem mathematically different. We have S times what we have here squared. So this gets a little bit more complicated, right? I have an issue there with the complexity of that one, okay? So sometimes these problems can be a little bit tricky, and we're not going to go through figuring out the molar solubility of a compound where we have to deal with s to the third power, okay? So we're not going to look at that one, all right? But I do want to show you one more issue. And that would be, for example, suppose we take the salt barium fluoride and try to dissolve that one. Barium and 2 fluorides. So our KSP would be the concentration of barium times the concentration of fluoride squared, right? Ba2 plus 2F minus. Okay. Now suppose that when we look at this, we consider this ion right here, the F minus. Okay. Suppose we make the solution acidic. This is something we do. We make it acidic. Okay? If we make it acidic, it turns out that the fluoride ion is the conjugate base of a weak acid. Okay? So what happens is, if we make it acidic, the fluoride will react with the hydronium ion to give us HF and water. Okay? Now the effect of that is that by making the solution acidic, the fluoride ion is reduced in concentration to form HF. And so the effect of that then is that when we look at the equilibrium here, this concentration is going to go down. We're reducing the fluoride from the solution. Okay? If you reduce, according to Le Chatelier's principle, if you reduce this concentration, what happens? If you remove it, the reaction is going to try to replace it, right? It's going to try to counteract the change you're making. So the result of this is that more dissolves. So if you have as one of the ions in the compound, if it's the conjugate base of a weak acid. So if it's a conjugate base of a weak acid, acidifying the solution results in more of the compound dissolving. Okay? It's got to be the conjugate base of a weak acid. It wouldn't work for a strong acid, but it will work for a weak acid, the conjugate base of a weak acid. So let me show you a little diagram here. Hopefully this will help you kind of understand it physically or chemically what's happening. You've got this barium fluoride, so we're going to take this barium fluoride. That's a solid. And some of it's going to dissolve. So there's going to be a little bit of barium in here and some fluoride. But now we're going to acidify it. We're going to add hydronium by adding hydrochloric acid or something like that. We're going to make it more acidic. By making it more acidic, the fluoride will react with the hydronium ion to give you HF and water. So if you've reduced this fluoride, now Q is less than KSP, so more of this will dissolve. Okay? So that requires that this be a conjugate base of a weak acid. So it would work for fluoride. So if we had a salt that had fluoride in it, if we had a salt that had nitrite in it, or cyanide, those are examples of conjugate bases of weak acids. So acidifying those solutions would form the weak acid and increase the solubility. What we'd observe is if you had chloride or bromide or iodide, for example, or nitrate, these are conjugate bases of strong acids. So there would be no effect, because what happens is when you add hydronium to chloride, or any of these, you get no reaction, right? So it wouldn't have any effect on any salts that had chloride, bromide, iodide, or nitrate, for example. Okay? So those are several, or a couple different ways we can affect the solubility. The pH affects the solubility of some. The common ion effect definitely affects the solubility of compounds. So take a look at some of the practice problems, the sample problems.